Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD, side AD of this rectangle equals to 3 units. Inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units in its length, and the radius of this small semicircle is equals to 1 unit. Our mission is to find out the length of this line segment AE. Okay, so first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles are all right angles. So this angle is a right angle. This is also a right angle. This is a right angle. This is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point P. We will define the center of this small semicircle. This point is point Q. We will define the touching point of those two semicircles. This point is point S. Likewise, we define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we will extend side DC and line segment AE by a straight line until they touch each other. Okay, this is their touching point. We define their touching point. This point is point F. Actually, we know that DC is one side of this rectangle ABCD, and therefore it is absolutely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. Okay, the result is DF. So, when you extend a straight line by a straight line, the result must be a straight line. So, therefore, DF must be a straight line. So, we'll focus on the upper side of this straight line DF at point C. Here, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle, it is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. So therefore, this missing angle must be equal to 90 degrees in its size. Okay, this angle is a right angle. So in the small right angle ECF, we define this angle as alpha. So in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll focus on the big right triangle ADF. In the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. PL is the radius of this big semicircle that is equal to 2 units in its length according to what is given as a question. The radius PL is known to point L, that is the point of tendency of tangent AE with this big semicircle. So here we will implement rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we also have here tangent AB. Tangent AB is tangent to this circle at this point, point M. In addition, we have here the radius OM. The radius OM that equals to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 1. So, we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL of this big semicircle that is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG. The radius QG that is equals to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in the small right triangle QGF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we will prove that the big right triangle LPF is similar to this small right triangle GQF. So I write it down. So we prove that the big right triangle LPF is similar to this small right triangle GQF. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle PLF in the big right triangle LPF, and it is equal to this angle, that's actually angle QGF. This one right triangle FGQ. So I'm repeating that. Actually found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle FGQ. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle GQF, it will be defined as angle GFQ. So I'll repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle PLF, and it is equal to this angle, that is actually angle GQF. In the small right triangle FGQ. So repeat again, we found out that angle LPF in the big right triangle PLF equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually proved that all the figures in this big right triangle LPF are correspondingly equal to all the figures in this big small right triangle GQF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. I proved that the big right triangle LPF is similar. This is the sign of similar to the small right triangle GQF according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LP in the big right triangle LPF over side GQ in the small right triangle FGQ equals to side PF in the big right triangle LPF over side QF in the small right triangle FGQ. So I think again, we derive that side LF in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP equals to 2 over GQ. GQ equals to 1 and it's equal to PF. So first of all, we know that DP and PS, they are there on this semicircle, and therefore each of them is equals to 2 units. So I write it down. DP equals to 2 units in its length. PS also equals to 2 units in its length. Likewise, QS and QC, they are there of this small semicircle, and therefore each of them is equals to 1. So I write it down. We define the length of this line segment CF as x. Again, CF equals to x according to our definition. So what is the length of side PF? Side PF in total equals to 2 plus 1 plus 1, that is 4, plus x. Again, side PF in total equals to 2 plus 1 plus 1, that is 4, plus x. So side PF in total equals to 4 plus x. Over side QF. QF in total equals to 1 plus x. Again, QF equals in total to QC, that is 1, plus CF, that is x. So QF in total equals to 1 plus x. So if I found out that 2 equals to 4 plus x over 1 plus x. So here we'll multiply this equation by 1 plus x, and we get that 2 times 1 plus x equals to 4 plus x. Here we'll open the brackets on this side of the equation, and you get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and you get that 2x minus x is x. So in this side of the equation we have x plus 2 is equal to 4. So x plus 2 equals to 4. Here we subtract 2 from this equation, and finally we get that x equals to 4 minus 2, that is 2. So x equals to 2 units in its length. Okay. CF equals to x, that is equal to 2 units in its length. In the next step, we prove that the biggest right triangle ADF is similar to the smallest right triangle, triangle ECF. So write it down. And then again we prove that the biggest right triangle in this drawing, that is triangle ADF, is similar to the smallest right triangle in this drawing, that is triangle ECF. So y, the biggest right triangle ADF, is similar to the smallest triangle ECF. First of all, those two angles, they're both equal to 90 degrees, and therefore they are equal to each other. So actually this is triangle ADF. In the big right triangle ADF, and it is equal to this angle, that is actually angle ECF, the small right triangle EFC. I'll repeat again. Actually found out that angle ADF in the big triangle equals to angle ECF in the small triangle. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it belongs to the big triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to angle alpha as it belongs to the small right triangle ECF, it will be defined as angle EFC. So repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees once alpha, therefore they are equal to each other. So actually, this is angle DAF. In the big right triangle AFD, and it is equal to this angle, that is actually angle CEF. In the small right triangle ECF. Repeat again, angle DAF in the big right triangle AFD equals to angle CEF in the small right triangle ECF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles inside the big triangle ADF are correspondingly equal to all the triangles in this small triangle ECF, and therefore those two triangles are similar to each other according to angle similarity rule. So I write it down. So the big triangle ADF is similar. This is the sign of similar to the small right triangle ECF according to angle similarity rule. And for the fact that the big right triangle ADF is similar to the small right triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AD in the big right triangle ADF over side EC in the small right triangle ECF equals to side DF in the big right triangle in DF, or side CF in the small right triangle in CF. So, I'll repeat again. We derive that side AD in the big triangle over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 4 units in its length according to what is given as the question over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF total equals to 2 plus 2, that is 4, plus 1 plus 1 plus 2, that is in total 8. Again, 2 plus 2 plus 2 is 6, and here we have 1 plus 1 is 2, and 6 plus 2 is 8. So DF in total equals to 8 over CF. CF is 2. So in Korean we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So if we found out that 3 over EC equals to 4. Here we multiply this equation by EC, and we get that 3 equals to 4 times EC. Here we divide this equation by 4, and finally we get that the missing side EC equals to 3/4 or 0.75 units in its length. So this is the missing side CE, that equals to 0.75 units in its length. So what is the length of this missing side BE? From the drawing it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So I write it down. If you found out that BE equals to BC minus EC. What is the length of BC? We know that ABCD is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So BC equals to 3. So in total, BE equals to BC, that is 3, minus EC. We just right now found out that EC equals to 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. And again, we should find out that BE equals to 2.25 units in its length. So this is side BE, that is equal to 2.25 units. Here, we know the symbol that the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. What is the length of DC? DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So in total, DC equals to 6. And according to the rule that the opposite sides of a rectangle are equal to each other, side AB equals to the opposite side DC. DC is 6, therefore AB must be also equal to 6 units in its length. So in the next step, I'll copy the right triangle ABE in a new page, and we'll implement the Pythagoras theorem on this right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a abbreviation for Pythagoras theorem. Again, side AB equals to 6 units in its length, and side B equals to 2.25 units. So here, this is the right angle ABE that is according to the original drawing. According to the Pythagoras theorem, in this right angle ABE, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AE, therefore the square of the hypotenuse is AE squared, and AE squared must be equal to AB squared plus BE squared. So I write it down. So in this right angle ABE, AE squared equals to AB squared plus BE squared. AE is the missing side, so we leave it as it is. So AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. So we can find out that AE squared equals to 36 plus 5.0625 is equals to 41.0625. So in conclusion, we can find out that AE squared equals to 41.0625. Here we take out all of this equation and find again that AE, that is the line segment that we're looking for in this question, is equals to the square to 41.0625. That actually equals to 6.408 units. And that is the answer to the question. Repeat again. And so we found out that the length of this line segment AE is equals to 6.408 units. So in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. We know that side AD of this rectangle is equals to 4 units in length. Inside this rectangle, we have those two semicircles. The radius of the big semicircle, this big semicircle is 2. The radius of this small semicircle is 1. And our mission is to find out the length of this line segment AE. So first of all, we know that all the 4 angles in this rectangle are right angles. In the next step, we actually defined the relevant points to this question with letters. We defined the center of this big semicircle, this point is point P. We defined the center of this small semicircle, this point is point Q. We defined the touching point of those two semicircles, this point is point S. We defined the point of tendency of tangent AE with this big semicircle, this point is point A. And finally, we defined the point of tendency of tangent AG, of tangent AE with this small semicircle, this point is point G. In the next step we did the construction, that is to say, we extended side DC of this rectangle and side and line segment AE by straight line until they touch each other. This is the touching point. We define the touching point as point F. So DC is one side of this rectangle ABCD, and therefore it is absolutely a straight line. And then we extended the straight line DC by straight line, and the result is DF. When we extend the straight line by straight line, the result must be a straight line. So DF is also a straight line. So if we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle, that is the right angle, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we defined this is angle F. We define this angle F as alpha. So in the right angle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 equals to 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule, then the sum of the angles in any triangle is equal to 180 degrees. We know that PL is the radius of this big semicircle that is equal to 2 units in its length. The radius PL is going to point L, that is the point of tendency of tangent AE in this big semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG that is 1 to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay, so in this small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that the right big triangle LPF is similar to this small right triangle QGC. Again, we proved that the right big triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the angles of the big right triangle LPF are correspondingly equal to all the angles of the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP in the big triangle or side GQ in the small triangle equals to side PF in the big triangle or side QF in the small triangle. And repeat again, we will derive that side LP in the big triangle or side GQ in the small triangle equals to side PF in the big triangle or side QF in the small triangle. LP is the radius of the big semicircle, that is 2. GQ is the radius of the small semicircle, that is 1. What is the value of PF? PF equals to 2 plus 1 plus 1, that is 4, plus x. Again, PF equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x over QF. QF equals to 1 plus x. So we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and finally found out that 2 times 1 is 2, plus 2x equals to 4 plus x. Here we subtract x from this equation, and finally found out that here 2x plus x is x, so in this side of the equation we have to leave with x plus 2, that is equals to 4. So x plus 2 equals to 4. Here we subtract 2 from this equation, and finally found out that x equals to 4 minus 2, that is 2. So this line segment CF, that is equals to x, is equals to 2 units in itself. In the next step, we proved that the big right triangle ADF is similar to the small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so you can write out that the angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you prove that all the triangles of the big right triangle ADF are correspondingly equal to all the triangles of this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that the right big triangle ADF is similar to the small right triangle ECF, we derive that the following relationship exists between their sides. We derive that side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. Repeat again. We derive that side AD in the big triangle ADF or side EC in the small triangle ECF equals to side DF in the big right triangle ADF or side CF in the small right triangle ECF. AD is 3 over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2, that is 4, plus 1, that is 6, plus 2, 6 plus 2 is 8. So in total DF equals to 8 units in its length over CF. CF equals to 2. So in conclusion, we can found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So in total we found out that 3 over EC equals to 4. Here we multiply this equation by EC, and finally found out that 3 equals to 4 EC. Here we divided this equation by 4, and finally found out that the missing side EC equals to 3/4 or 0.75. So okay, this is the missing side EC, that is equals to either 3/4 or 0.75 units in its length. What is the length of this missing line segment BE? The length of the missing line segment BE will be equal to BC minus EC. Again, BC minus EC equals to BE. Repeat again, BE equals to BC minus EC. What is the length of BC? You have to again ABCD, the opposite sides are equal to each other. That is to say, side AD equals to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. So BC equals to 3 units in its length. And so in total, BE equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. Then again, if we found out that the missing line segment BE is equals to 2.25 units in its length. Here we use the same rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC. But what is the length of DC? DC in total equals to 2 plus 2, that is 4, plus 1, that is 2. And 4 plus 2 is 6. So DC equals to 6, therefore the opposite side AB must be also equal to 6. In the next step, I copied the right triangle ABE in a new page and implemented the Pythagoras theorem on this right triangle ABE. Side AB equals to 6 and side B equals to 2.25. The hypotenuse is the missing side. Okay, this is the right triangle ABE. Then I'm going to form the regular domain. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABE is AE, and therefore the square of the hypotenuse is AE square, and AE square must be equal to AB square plus BE square. AE is the missing side, so we leave it as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36. Plus BE square. BE is 2.25, and therefore BE square is 2.25 squared, that is 6.0625. So in total we found out that the AE square equals to 36 plus 6.0625. 36 plus 6.0625 equals to 41.0625. Here we took out of this equation and finally found out that the missing 97 AE equals to the square root of 41.0625, and the square root of 41.0625 is 6.48 units. So in conclusion, we found out that the length of this 97 AE is equals to 6.408 units. Okay, thank you very much.